This question is asking the PMOS transistor in the CS amplifier of figure P7.119 has VTP is equal to minus 0.7 voltage and a very large VA. Select A bar is asking select a value for Rs to bias the transistor at ID is equal to 0.3 milliampere and V over drive is equal to 0.3 voltage. Assume vsig to have a 0 DC component. And the B part is asking select a value for RD that result in GB is equal to minus 10 voltage per voltage. This is a gain. And here we have the diagram provided, and the C part is asking find the largest vsig that the amplifier can handle while remaining in the saturation region. What is the corresponding signal at the output? And the D part is asking if to obtain reasonably linear operation vsig is limited to 50 millivoltage, what value can RD be increased to while maintaining saturation region operation, and what's the new value of GB? Now let's go ahead and do one by one. So let's look at the A part. In the A part, the question is asking select the value for the Rs to bias the transistor at ID is equal to 0.3 milliampere and V over drive is 0.3 voltage. Assume vsig to have a 0 DC component. So here what we have to do is we have to find out the Rs value, and ID value is provided, that is 0.3 milliampere, and also we have the V over drive, that is 0.3 voltage. Okay, now in order to find out Rs value, first we can find Vs value, and then we can do the KVL, Kirchhoff's voltage law, right here. If we do that, we can solve for Rs. So in order to find a Vs, the first thing is we can find out vsig. To find out vsg, I had to know vg. Okay, so calculate vg is gate voltage. Calculate the gate voltage. Gate voltage, and Vg is given by Ig times Rsig, and this is a PMOS transistor. So for PMOS transistor, there's no current flow in the gate, so the Ig is 0. So we can say since Ig is equal to 0, that's gonna make Vg to be 0, because if we plug 0 for Ig, that's gonna turn into 0. Okay, if Vg is 0, then vsg, we can find vsg. Vsg is given by VTP, that is V threshold for PMOS transistor, and then V over drive, absolute value. And VTP is given in the question right here, and V over drive also given, and both of them are absolute value. So if you have a negative, that will turn into positive. So let's plug the value 0.7 for the VTP, and then V over drive is 0.3. altogether it makes up to 1 voltage, and we know that Vg is, we solve the Vg to be 0 over here. Okay, and vsg is basically Vs minus Vg is equal to vsg. So Vs minus 0 is equal to vsg. Therefore vsg, if vsg is 1 voltage, then Vs is also 1 voltage. Okay, now we have Vs. Now we can go ahead and apply Kirchhoff's voltage law here and solve for Rs. That's our first question. Now let's go ahead and apply KVL. So if I apply KVL over there, here we have 2.5 voltage, so let's put that one right here. 2.5 is equal to, we have Rs resistor, and the current flow through this one is ID. So that is equal to Rs times ID, and then plus Vs. Okay, this is the KVL, and here we have the ID available that's provided in the question, 0.3 milliampere. And also Vs, we just solved that one. We just found out Vs to be 1 voltage, plug it all in, and we can solve for Rs. And if we rearrange this equation, that's going to look like this. Rs is equal to 2.5 minus Vs, and then I divided by ID. 2.5 minus Vs is 1, and then ID is given in the question, that is 0.3 milliampere. So this one is like 1.5 divided by 0.3 milliampere. This one is voltage. So milli become kilo when it's go to the top, and then 1.5 is basically 5 times of 3, so 0.3. So this is going to be 5 kilo ohm resistance. That is our Rs. That is the A part of the question. And now let's go ahead and see the B part. The B part is asking select a value for Rd that result in Gv is equal to minus 10 voltage per voltage. That's the gain. Now here you have Gv provided. We have to find out what's the Rd. Now in order to deal with this one, we have to find out the transconductance, because there's an equation given for Gv is like that. Gv is given by V0 over vsig, that is also equivalent to minus Gm Rd. And this is the second one is helpful for us because we have Gv available. We can find the Gm, that is transconductance. To find the Gm, there is an equation that is 2Id divided by V overdrive, and we have Id available, that's the drain current, and also overdrive also provided in the question, so we can plug it all in and find the value. So Id is 0.3 milliampere, so 0.3 times 10 to the power minus 3. 3 milli is 10 to the power minus 3. We are converting everything to SI unit. So, and then V overdrive is also given in the question. If you notice here, it's already a 0.3. So I can plug that one as well. And then 0.3 cancels, and then we end up getting 2 milli for the transconductor. The transconductor is basically given by ampere per voltage. So this is milli is still there, so we can write 2 milliampere per voltage. This is our transconductance. Now we can apply in this equation and solve for Rd. And Gv, the expected Gv is given in the question, that is minus 10 voltage per voltage. So plug that one in. So I'm bringing this equation, Gv is equal to minus GMRD, and Gv, for Gv I plug 10 voltage per voltage, and then minus GM, okay, let's put that one, and then minus GM is minus 2 milliampere per voltage, and then Rd. So if we rearrange the minus cancels each other, and then 10 divided by 2 we get, and also milli becomes kilo when we go to the top. So here we're gonna end up getting 5 kilo ohm resistance for Rd. That is the B part of the question. Okay, and the C part, let's look at the C part. And the C part is a question asking find the largest sinusoid vsig that the amplifier can handle while remaining in the saturation region. What is the corresponding signal at the output? Let's do that. So to maintain a transistor in a saturation region, there's an equation that is VST should be, source drain should be, source drain minus vsig should be greater than V threshold of PMOS transistor. And this one also can be written as VO dash plus VO dash over GV plus VGD greater than VTP. Let's call this one equation number 1. and VGD is nothing but VG minus VD. And VG, we already solved the VG in the first part of the question, that is 0, because in the gate there's no current, therefore VG is going to be 0 for the PMOS transistor. So we can just plug that one in over here. Therefore we can say that VGD is equivalent to minus VD. Okay, so now we have this one, and here we can solve for VD by applying the Kirchhoff's voltage law at the drain over here. Here we have a minus 2.5 voltage RD, and the current flow through this RD is ID, and that the whole thing is going to be equivalent to VD. Okay, so let's write that one down here. So if I apply Kirchhoff's voltage KVL over there, that's going to be VD minus IDRD is equivalent to minus 2.5. Therefore VD is going to be equivalent to IDRD minus 2.5. Therefore if we solve for VD, we end up getting minus 1 voltage, and ID is 0.3 milliampere. RD we already calculated over here, 5 kilo ohm. So you plug that one all in and solve for VD, you end up getting minus 1 voltage there. Okay, and then once you have that, then you can go back to this equation right here. Okay, and instead of VGD, put minus VD. And VD is minus 1 voltage. So when we put it here, that's going to be minus 1, that's going to turn into plus 1. Let's rewrite that one. So if I rewrite that equation, that is VO bar is plus VO bar over GV. GV also we know that minus 10, but it's in the absolute value, so that we can put 10 here, and then plus 1, that should be greater than or equal to minus 0.7. Therefore V0 max should be equivalent should be greater than or equal to 1.55 V peak. Okay, the sign flips because of this negative sign, this this expression. Okay, and we are not done yet. So that is therefore vsig max, that's VO max. So vsig max is VO max divided by GV. And VO max is 1.55 V peak divided by 10. 10 is the gain. So that's going to end up being 0.155 V peak. And that's our final answer. And the D part is asking if to obtain reasonably linear operation vsig is limited to 50 millivoltage. What value can RD be increased to while maintaining saturation region operation? What's the new value of GD? Okay, now let's do that. Okay, here I'm going to do the D part for using limited to 50 voltage, actually 50 millivoltage, limited to 50 millivoltage. The change in drain resistance R D can be found from equation number 1. Can be found from equation number 1 that we introduced over here. Okay, rewrite that equation. Let's put that one here. Minus V0 plus VO divided by GV plus VGD is greater than or equal to VTP. And here we can do one thing, that we can make this denominator common by multiplying top and bottom by GV for this one. If we do that, we end up getting this GV plus 1 over GV, and then we can take the V naught outside of the we can take the V naught common here. This V naught bar and the others remains the same. VGD, that's greater than or equal to VTP. Okay, and here we have to substitute GV vsig for V naught bar. If we do that, then this equation becomes GV plus 1 over GV, and this GV V naught becomes GV vsig plus VGD, that's greater than VTP. Okay, let's go to the next one. Let's continue. So, and VGD also, we found an expression for this over here. VGD we did somewhere here. Yeah, VGD is equal to minus VD, and VD is given by this. If VD is this one, then minus VD is going to be 2.5 minus IDRD. Okay, so we can plug that one instead of VGD. Minus 2.5 minus IDRD becomes VGD. Okay, so here we are right now. Instead of VGD, we are going to do that. So let's go and do this. If we do that, then this equation becomes, and also instead of GV we can put minus GMRD also, because the transconduction equation is given by this GV is equal to minus GMRD. We can do that on ourselves. So if we rewrite the equation in terms of that, then the whole thing become minus GMRD plus 1 divided by minus GMRD, and then minus GMRD times vsig plus, instead of VGD we put 2.5 minus IDRD and that should be, the whole thing should be greater than VTP. Okay, this is that, and what else? We can remove the negative sign if you want. We have a negative in the denominator, and here we can cancel each other and make both of them positive. So if you do that, this is going to become minus GMRD plus 1. In the denominator we will have GMRD, and then in the outside also GMRD vsig, and then plus 2.5 minus IDRD. the whole thing should be greater than VTP. Okay, now the next thing is we have to just substitute the values. The available values we have 50 millivoltage for the vsig. Let me label this. So we know that vsig, according to the question, that is given by 50 millivoltage, and we have ID current to be, drain current is 0.3 milliampere provided in the question, and then we have GM, the transconductance. Also we know that is Alexa stop, and also we know the transconductance, that is 2 milliampere per voltage, and also we know the V threshold for the PMOS VTP, that is equal to minus 0.7 voltage. So we have all these value for this, and we have to just solve for the RD. In this case, RD is the only unknown here. So if you solve for the rearrange and solve for RD, you will end up getting RD to be less than or equal to 8.125 kilo ohm resistance. Okay, once you have the RD, then now you can go ahead and find the new gain, that is GB is equal to minus GMRD, and then GM remains the same, that is 2 times 10 to the power minus 3 10 to the power minus 3 ampere per voltage times the RD value, that is 8.125, and kilo is 10 to the power 3, and finally we will end up getting minus 16.25 voltage per voltage, and that's our final answer. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my